Es un poco con los fines, ¿no? De que conociéramos, la gente que conociera lo que hacen, pues sería bueno que lo diera. Hay audiencia en el Senado, poca audiencia. Muy bien, pues vamos a iniciar el coloquio de hoy. Tenemos el gusto de tener a Ana Lilia Longinotti de la Agencia Espacial, ¿no? en Madrid. Ella hizo su maestría en Bolonia, en Italia, el doctorado en el Imperial College en Londres y actualmente luego hizo un postdoc en Madrid y actualmente es support scientist en la Agencia Espacial Europea. Y nos va a hablar parte de su trabajo, que es gas circumnuclear en núcleos activos de galaxias, la perspectiva en rayos X. Adelante, por favor.
Muchas gracias y también les voy a saludar a los de Ensenada allá. Y también quería agradecer la oportunidad de dar este coloquio aquí. Me voy a disculpar porque este coloquio para mí no estaba previsto, porque yo estoy aquí de vacaciones, entonces va a resultar algo improvisado tal vez. Y también porque lo voy a dar en inglés, que me viene mucho más cómodo. De todas formas, os pido que si tenéis dudas, preguntas durante el coloquio, claramente que me interrumpan y pregunten, no hay ningún problema. Pues, so today I'm going to talk about the X-ray perspective of AGN and the circumnuclear gas in AGN. And first, I would like to acknowledge my main collaborators, Matteo Guainazzi e Ignacio Della Caia at ESAC, Stefano Bianchi and Giorgio Matte at Roma Tre University in Italy, my student Damien Coffey, who's now at Trinity College in Dublin, and Jair here, Jerry Chris at Space Telescope Science Institute in Baltimore, and Dirk Krupp at Penn State. So, outline of my talk, I will give a general introduction on AGN properties, starting from the central engine and accretion processes. Then I will concentrate a little bit more on some work that I published together with Ignacio Della Caia, which is focused on relativistic objects, relativistic ion lines in AGN. Then I will continue the journey through outer region in the AGN, and I will describe the X-ray view of the circumnuclear cold and photoionized gas at all scales, the narrowline region, torus, the broadline region, finishing with accretion disk winds. And can you hear me? And here, with regards to accretion disk winds, I will concentrate more on a recent work that is published now, and which is the emergence of an accretion disk outflow in these Seyfert galaxies. So just for the people who are not familiar with X-ray facilities, this is a list of the X-ray facilities that are now working. XMM-Newton and Chandra are the only ones who are equipped with X-ray grating spectrometers, so they are capable to produce high-resolution data. Swift is very efficient for monitoring variable sources, and it's equipped with CCD. In the XRT telescope, the band is the same as Chandra and XMM-Newton for the CCD, so 0.5 to 10 kV. And then Suzaku and NUSTAR have extended the bandwidth to hard X-rays at 40 kV and 80 kV. So what is an AGN? I guess everybody knows what is an AGN. The name quasar comes from quasi-stellar radio objects. They appear as stars. They have this very wide spectral energy distribution. We now know that, oh no, okay. We now know that the enormous energy output comes from accretion on a supermassive black holes. We know that this supermassive black hole is surrounded by some cold material and obscuring material in a torus shape. We know that some AGN have powerful jets as well. And what we know about this central region that produces all of these energies is that because the variability of the X-ray and the gamma ray emission is happens in a very short time scales, we know that this region is very compact and very small, so with a radius of less than 10 to the 15 centimeters. So let's have a look closer to this central region in AGN. And for doing that, we need X-rays. We need high energy radiation because it's the only one that is able to come out from all of the gas that is surrounding this region. So here on the right side of the screen, I put the typical X-ray spectrum of a Seyfert I galaxy. It's just a sketch. These are not data yet. It's just the model. The typical shape of the X-ray spectrum, 0.1 to 100 keV. So this is basically the whole energy band. Most of the data that I will show in this talk stop at 10 keV because the bandwidth of XMM and Chandra are finishes at 10 keV, so we are basically concentrated here, but the X-ray spectrum extends at larger energies. So what we think is that the supermassive black hole is surrounded by an accretion disk, which is coupled, in a sense, with a hot corona. We call this gas hot corona, and it's made by relativistic electrons. And the photons, the UV photons emitted by the accretion disk, interacts with the relativistic electron in the hot corona, and by Compton scattering, they produce a spectrum in form of the of a power law with a typical slope of equal to photon index equal to, which is plotted here. Now, this primary power law, which comes out from the central engine, then it's upscattered by Compton scattering here, and this is the Compton hump, which I will explain better in the next slide. And then this primary power is also absorbed sometimes by intervening gas, and here you see a rise of the spectrum, which we call usually soft excess, which is probably the high energy, the energetic part of the typical big blue bump of AGN. On the right side, there's the usual sketch, the usual model that we have in mind for describing AGN. So just for scale, all the black hole and accretion disk system is concentrated here, and it's surrounded by a torus-shaped material of cold gas. And here are the radio jets, of which I'm not going to talk about in this talk, the narrow line region and the broad line region, but this will be explained better next. 10 to the 9, more or less. Mm-hmm. Compton scattering of the UV photons. Yeah. So the Compton reflection is one of the main features that we see in the spectrum of the AGN. The primary power law that I described before is reflected by some neutral optically thick slab of material, and it gives rise to the typical reflection spectrum, which was first described by George and Fabian in 1991, and of which is characterized by fluorescence emission lines, as you see here, and this typical Compton hump shape. Now, just for showing some data, finally, these are real data from XMM-Newton. This is 5 to 10 keV. This is the Circumnuclear galaxy, so it's an obscured AGN. And what you see here is the typical iron K alpha and iron K beta line that you see here in the model, the nickel iron K alpha line, and then this is just this little part here, which is the photoelectric absorption that causes the iron edge here. The fluorescence yield is maximum for iron, so this is why this line is the most prominent in AGN. And what is this slab of material that is that produces the Compton reflector? What is this reflector? Well, the Compton reflection spectrum is the main evidence in X-ray for the presence of the Compton-thick torus, which is distributed on a parsec scale around the AGN. The torus has also been studied very much in infrared wavelength, and infrared, thanks to infrared interferometry, it was revealed and measured in the Seyfert II galaxies NGC1365 by Jaffe et al. But here I'm going to tell you about the main evidence in X-rays. For example, The iron K alpha line is basically ubiquitous in all AGN. This is a compilation of spectra from the Chandra HETG gratings. Here in color is highlighted the emission line, here, the iron K alpha line. And this is a sample of Seyfert I galaxies published by Stefano Bianchi in 2007. Here, what I'm plotting is the iron K line equivalent width, so basically the intensity of the iron line, and the 2 to 10 keV luminosity, so the luminosity in X-rays. And so you see very clearly an anti-correlation of the intensity of the iron line with increasing luminosity, which is probably, very much probably, due to the opening angle of the torus that reduces, basically, the opening angle of the torus that increases at high luminosity and reduces the intensity of the iron line. Now, this leads me to unification model, because the torus is the key ingredient of unification models. We know very well since very many years that in optical there is a very clear dichotomy of AGN, of properties of AGN, with Seyfert I galaxy showing only broad optical, Seyfert I galaxies showing narrow and broad optical lines in the optical spectra, and Seyfert II only showing narrow optical lines, so with full width of maximum below 1,000 kilometers per second. And this is explained with orientation effect. So if we are looking at the AGN from this angle, we see both the region, the broad line region, which is producing the broad line, and both the narrow line region, which is much more external, which produces a narrow line. But if we see on this angle, along this line of sight, we only see the narrow line region, and so this produces a typical Seyfert II spectrum. This explanation works very well also in X-rays, because we see here the spectral energy distribution of AGN taken by BEPOSAX in the basis 500 kV. So you see that below 10 kV, the two spectral energy distributions are very different, because Seyfert IIs are very much absorbed here. And this absorption is shown below. This is the effect of increasing column density that basically reduces. The spectrum emerges only above some energy like 8 kV, and everything else is absorbed before at shorter wavelength. And the absorbing material is the torus that is also responsible for this narrow line and broad line dichotomy. Now, let me go back to the iron K emission in AGN. These have been the features that have been studied a lot, because in the years, because they are the most prominent. So I said before that that the iron K alpha and K beta line comes from fluorescence, from iron, from neutral iron, and so they are produced in the parsec scale torus by Compton reflection. But we see also that there are ionized line by iron 25 and iron 26 at 6.7 and 6.97 kV. These are very evident in the spectra that I'm showing here. These are two spectra. This is from XMM-Newton, this is from Chandra, and this is a work that I've been done in the past. These are just data to model ratios, so basically all the residuals are due to emission lines. And you see very clearly the neutral iron line, the iron 25 and iron 26 line. And these two ionized lines come from circumnuclear warm gas. This is different from the torus. Now, for many years, since the 90s, the iron K line have been at the center of a very lively debate, because when the Compton reflection takes place on the accretion disk, on a slab of cold material, which can be the accretion disk around the supermassive black hole, then relativistic effects induced by the gravity of the supermassive black hole take place, and the profile of the line gets skewed and asymmetric and broadened by all of these effects, the combination of all of these effects. And so we have this very broad and iron line, which have been at the center of a big debate, which I'm going to talk about now. Now, this is all the theory in a very compressed way. There are many reviews by Andy Fabian, Chris Reynolds, Mike Novak in the past, if you want to read more. What I want to show here is data. Again, these are data to model ratio, XMM data fitted only with a power law, so everything that you see in residuals is due to line emission. And this is the most famous example of an iron line, the iron line in MCG1365. And you see here that this is the core of the iron line, and you see what we called normally the red wing, which is basically the gravitational redshift shape here. Below, and you see 7469, this is another Seyfert I galaxy, which is very similar to the other one, but you see only the narrow core of the line. So basically, the quest for iron line in many AGN has lasted and still lasts for the recent 20 years. People are still very much discussing about it. And I will tell you why. Why do we care so much? Because they are probe of strong gravity, so they probe relativistic effects and in supermassive black holes, because they are all common also to X-ray binaries, not and accreting compact objects on galactic scales. So, for example, this is a collection by Ed Cackett in 2009, and these are data to model ratio of low mass X-ray binaries in the iron K-band. And you see again this skewed and broadened profile. So there was a lot of discussion also in that community, not just in AGN. They provide diagnostic of accretion destructure. They have the potential to measure the black hole spin, which is also very important for models of black hole growth at a high redshift universe. So, for example, just to show, these are 3 different profiles at different disk inclination angle, 10 degrees, 30 degrees, 70 degrees. And these are the 2 profiles for a non-spinning black hole and the spinning black hole. This other one here, which extends much further down in energies. Some history, very quickly. I said that they have been studied a lot in the past. In ASCA, they were very common, and then when XMM came, it wasn't very clear if all AGN were characterized by this line. For example, Elena Jimenez published this sample of quasars observed by XMM-Newton, and the broad lines fraction was only 10%. And in XMM individual sources, they were found very often, but always by different people. There wasn't an homogeneous sample, let's say. And the main competing models for producing these residuals in the spectra were basically a complex line of sight absorption with very high ionization parameter and column densities, and also blending of ionized iron line. So this brings me to talk about the survey that with my group at ESAC we built for basically answering 2 questions. How often do we see relativistic lines in AGN, and are they related in any sense with properties like intrinsic properties like black hole mass, X-ray luminosities, accretion rate, something like that? Is that the point was, is there any driver of these lines, or they just appear randomly, let's say? So this is a complex slide, but I just want to say that we took, this is the largest sample of radioquiet Type I AGN coming from the XMM archive. They are all defined to have a very low column density. We use only EPIC PN data. We combined multiple observations. The fit was done in the 2 to 10 kV res frame. The models that we used were the KY models developed by Michal Dovchak, and they were fitted very homogeneously, so there wasn't any uncertainty on calibration, data reduction, models, everything was done totally homogeneous. Now, this figure is the equivalent width, so the intensity of the iron line, versus hard X-ray counts. So basically, this is the signal to noise of our sources. And the green point marks the 5 sigma detection of an iron line. And you see that they are all concentrated at very high signal to noise. So this was the first, the first thing that we noticed is that we need very high signal to noise to detect very clearly iron lines. I prefer to go directly to the conclusions of this. In the reference sample that we identified within this big collection, basically we found a fraction of around 30% of sources showing a broad relativistic line. The mean equivalent width is found around 150 electron volt. We didn't find any trend with disk parameters, for example, with inclination. In general, we found that broad lines are weaker than what was thought before. They are all found for an inclination of the accretion disk around 30%, which is what is expected by the models. And when we tried to find what was the driver, we didn't find any particular correlation with the physical parameters of the source, although we still find that quasars, so higher luminosity sources, show weaker lines than in Seyfert. So probably the luminosity is the fact that the higher luminosity sources show weaker lines can tell that the driver may be the luminosity. And this is, I think, all that I wanted to say. No, sorry. This is a very nice recent result on the broad iron line, which is based on NUSTAR data, and it was published by Guido Risaliti in Nature last year. What I'm showing here is basically XMM and NUSTAR data. XMM are in light blue and NUSTAR data are in yellow. You have to think that up to now the bandwidth was, the accessible bandwidth was only up to 10 kV. So basically, the two competing models for describing these residuals, so gravitational distortion or complex gas obscuration, were pretty much coincident. So it wasn't possible to distinguish between these two models with data up to 10 kV. But NUSTAR opened up a new window because it's able to focus hard X-ray photons up to 60, 70 kV. And what you see here is that the NUSTAR data are all distributed along the model for gravitational obscuration. And so this has allowed Guido and his collaborators to say with very high confidence that these residuals are totally due to some relativistic effects, which are in this case produced by a spinning black hole, because the spinning black hole produced a better model than non-rotating black hole. So they were able to measure the spin in this case. And this is all that I wanted to say on relativistic lines. So we go on the second part of the talk, and we continue our journey in the outer regions of the AGN. And here what I'm starting with is the extended gas at parsec and kiloparsec scales around the AGN. So here what I'm showing are HST images in the oxygen 3 line with X-ray contours from Chandra superimposed. So the contours are from Chandra in these images, and the image is oxygen 3. Oxygen 3 is a tracer of the narrow line region, and so are also the soft X-rays from Chandra, as it was discovered once this work was finalized. These are taken by mainly by Stefano Bianchi's paper and also by Sacco and Young papers. So the comparison between the Chandra and HST images shows very clearly that the oxygen 3 and the soft X-ray are very much coincident. Their rush is fairly constant along with the radius, up to hundreds of parsec. With photoionization models, it was possible to reproduce this behavior if we assume that the electron density is scales with the squared of the radius. So this also means that the ionization parameter of this process, which is induced by the central engine, is constant along all of this distance. Now, when we take spectra of this region with high resolution, we see we see evidence for photoionization process in the X-ray even stronger. What I'm showing here is a combined spectrum from the XMM-Newton gratings, RGS gratings, and this is basically the stack of 33 of Seyfert II's spectra. This is 10 to 35 angstroms, so more or less it's below 1 keV. And what you see here, all of these sources are totally dominated by emission lines, and basically no continuum almost. The emission lines are from helium and hydrogen lying, oxygen, neon, carbon, and also narrow radiative recombination continua. So this was the further proof, let's say, that another proof that the soft X-ray spectrum of this AGN is totally dominated by photoionization. And photoionization, it happens in the narrow line region, and this was possible this conclusion was reached after doing line ratio diagnostic for all of these triplets that are seen here, and after measuring basically the density of this gas. And the density of this gas is very low, and it's very much in agreement with the narrow line region. This is just an example of one of the spectra. One of the best studied cases, NGC1365, which is the brightest Seyfert II, and it was observed several times. And I don't have the graph with me, but my group at MIT has now published the deepest Chandra grating exposure of 1068 in a paper by Tim Kalman, which was in the archive last year. What is the view of Seyfert I? Are they so clear and homogeneous as Seyfert II galaxies? Well, they are different. What I'm showing here in this animation is these are Seyfert I taken from the XMM archive, data to model ratio. You see here that the power law is very well fitted, but the extrapolation in the soft X-ray has always different shape for different sources. And this is because we have a direct view of the continuum, or the primary continuum, and its interaction with circumnuclear material. We know that in 50% of sources there are ionized absorbers, and we know also that there are variability phenomena at work. And this is much more evident here when we see multi-epoch X-ray spectra. This is very important now after that the X-ray missions have been and are still operating since almost 15 years, because we have a totally different view of some sources. It's not just static. For example, ISO 323-G77, this is taken by a paper where I'm co-author together with Yair by Giovanni Minuti. This source was published by Elena Jimenez. She published, I think, this spectrum here. And then after we added some other spectra, we found out that this source is very variable, as you see, and it's it's even more interesting than we thought before. The same for this other source, H0557, which is which was brilliantly studied by my student, Damien Coffey. What you see here again are XMM spectra from different epochs. And here I want to highlight that the variability between these states, this other state, and this other take place in a 4 or 5 years time scale, where everything that happens here is on a week's time scale. How do we interpret this behavior? Well, the clumpy torus model, which was developed by the group of Nankova and Elitsur for explaining infrared data, works very well in this case, also for X-rays, because basically what we think is that the torus is not an homogeneous wall of gas, but instead the inner wall of the torus is fragmented and clumpy. And so when these clumps pass through the line of sight, they produce all of this absorption. And even more interesting, there's probably a continuous distribution of clouds of gas between the broadline region and the torus, because basically the broadline region then it's contiguous to the torus. And it's something that we are also seeing in X-ray observation of variable sources. For example, this is another famous case published by Guido Risaliti, again NGC1365. The variability which takes place in 2 days in this source is explained by the eclipse of an X-ray source by an orbiting cloud located in the broadline region. And the location of the broadline region comes exactly from these very short time scales. So basically, we have different line of sight, and when one of these cloudlets crosses our line of sight, we have an eclipse. This is the idea. And so we are able now to see this clumpiness in the torus through X-ray spectra. I said before that absorption in Type I AGN is also due to ionized gas. So when the gas in the line of sight is ionized, what do we see? We see a spectrum which is more or less resembling this one. This is NGC1365. This is again data to model ratio. And you see these big, broad features below 1 kb. When we look at these sources with high resolution, we see a wonderful absorption line spectrum where we see neon, magnesium, sulfur, aluminium, again neon and iron. And this is what we call warm absorbers, because they are ionized as opposed to cold absorber. So these warm absorbers are present in about 50% of the Seyfert galaxy. They have outflow velocities in this range, 10 to the 2, 10 to the 3 kilometers per second. They present a wide range of ionization states, very many layers of ionizations. They have some column density around 10 to the 20, 10 to the 22. They are always associated to UV outflow. What we don't know very clearly yet is where are they. There are basically three main propositions. One is that they are originating in the narrow line region. One is that they originate in the inner wall of the torus. And one is that they are originated by accretion disk wind. And this was proposed, for example, by Jair in NGC4051 and by other people as well. So this leads me to the last part of my talk. I want to show a recent result that we got together with Jair, Jerry Chris, their group, and other people. And this is the emergence of an accretion disk outflow in this Seyfert I galaxy, Markarian 335. First, Markarian 335 is a source that has been observed many times in X-rays, and it never showed any X-ray absorber, and neither a UV absorber actually. And it's still been monitored by Swift since 2007. This is the light curve by Swift. These are the X-ray counts here. And thanks to this long-term monitoring, there have been 2 triggers of XMM, 2007 and 2009, and these 2 triggers has produced these 2 spectra. Basically, this is Markarian 355 in the normal state, high state, very very normal power law. But when we triggered this source in different states, we found an intermediate state here in 2009, and this is a very high, low state, which was observed in 2007. And I concentrated on explaining, studying this data more than the swift light curve. So when we look at this data with high resolution, because XMM can XMM yield both CCD and RGA and high resolution data at the same time, so we always have the high resolution data with XMM. What we see is that in the high state, basically we have just a very shallow absorber here. This is the RGA spectra between 14 and 20 angstrom, so this is all below 1 keV. When we looked at the intermediate state, we see a very clear absorption, which is due all to iron transitions, and we also see oxygen absorption here. So we modeled this data. This is the intermediate spectrum with our best fit model, and what we found is that this absorber is made by 3 ionization phases, which are these modeled here. These are the medium and high and low ionization phase that go in this model. The outflow velocity of this absorber is very high. It's much higher than in normal Seyfert I galaxies, around 5,000 kilometers per second. We didn't see change of the ionization parameters, so we couldn't explain the variability of this ionized absorber only with ionization changes. And this suggested that there must be some kind of partial covering absorption instead. Now, I said that the ionized absorbers are always accompanied by UV absorbers. Markarian 355 is a different case because actually it was the prototype of an active nucleus free from UV absorption. So it was with our largest surprise that when we looked at the COS data, HST COS data, which were taken in 2009 and 2010, we found some very shallow absorber here. This is the carbon-4 line. And it's much more evident if I put the HST history of the source. This is the velocity, the spectrum in velocity space. So basically, these are the velocity of the X-ray worm absorbers. Just for reference, this is 5,000 kilometers per second. And these are the data taken from HST in 2004, and these are the recent COS data. And what you see clear, this shallow and very broad carbon-4 line, which is much more evident in this data of October. Now, the XMM X-ray absorbers are from June 2009, so a little bit earlier than the HST observation. So we don't have actually still, we don't have simultaneous data for tracking these absorbers, but finally, we got an accepted trigger on XMM and HST together for next year. So we will probably have simultaneous data of this wind. And just to put it in context, the rising of UV outflows have been observed in other cases. For example, the narrow line Seyfert I, WPPS-007. You probably know the one that Yair published and on which he and Luke are still working on, TON 34, which show a transition from a normal to a broad absorption line quasars, and also very many cases, other cases. No, he published some more cases, but I mean other cases by Hamann. And all of these emergencies of UV outflows have been explained as some flow structure crossing our line of sight. So when this structure crosses our line of sight, we see this absorption. And so it's kind of rare. So our conclusion for describing what was happening in Markarian 335 is more or less the same, with the plus that we had the X-ray data as well. So because the UV absorption is slightly variable in between October 2009 and February 2010, we were able to locate these orbiting clouds at a distance consistent with the Broadland region of the AGN. And this is a viable interpretation also for the X-ray absorbers, because we know that the X-ray absorbers are not explained by ionization changes. So there must be some structure that also crosses the line of sight of the X-ray absorbers, or the X-ray radiation that produces that feature that I showed before. And this is the first time that this phenomenon is seen. I should say also that since the location is in the Broadland region, then the wind must originate in the accretion disk, because it cannot be outer. If we are locating everything in the Broadland region, then the wind is very probably originating on the accretion disk. And so this is the first time that this is seen also in UV data. Now, quickly, in earlier time, I had discovered other evidence for Broadland region gas in Markarian 335, and this was done by studying the very low state of the source, which at high resolution shows photoionized emission lines, very similar to the one that I showed for Obscured AGN. But in this case, the line ratios that we could measure were much more indicative of a Broadland region density. They were much more in the range 10 to the 9, 10 to the 11 centimeters to the power of -3. So so for the low state of the source, we proposed that there were some clouds in the Broadland region which were able to emit and scatter the X-ray emission and produces this iron line. For the future, how can we track? The question is, how can we track the worm absorber, coming back to the worm absorber in Markarian 335? Because what we know, what we need, is that we need some more refined time scale for locating it with more precision. So we're trying to see how can we track it. And we know the SWIFT is observing the source still. So we went to look at what SWIFT data look like, and this is a spectrum of SWIFT in the 0.5 to 5 kV. This is contemporaneous to the XMM data. So the XMM data where we see the absorbers. And even with the limitation of a short exposure and of a CCD spectrum, what you see here at 0.9-ish kV, this absorption feature, is what we think is the X-ray worm absorber seen by SWIFT. So everything that we saw here with this detail in XMM RGS, we see here now in SWIFT. So our idea, and this is something that we are doing now with Yair, is to measure this feature in all the SWIFT spectra and trying to see if there is some correlation or evolution of this feature. This feature is parameterized very in a crude way with an absorption edge. So we measure the optical depth, which is here optical depth, and this is the photon flux. So basically, the circle is the XMM-Newton observation. So the SWIFT contemporaneous to the XMM-Newton observation, and you see that the optical depth that we measure is quite high, whereas at higher fluxes, it drops. Basically, we have much less absorption, and this is still work in progress. So I won't go to conclusions here, but I'm just telling you how can we track these winds. This is just to show that this is the edge energy, so it's all concentrated around 0.9 keV, between 0.8 and 1 keV. So it's in very good agreement with the main RGS warm absorbent feature, and it's very constant, so it doesn't go everywhere in the spectrum. And finally, these are the SWIFT data starting from June 2008 up to January 2010. We are doing only the first chunk of data. Here again, I marked the SWIFT contemporaneous to the XMM observation. The blue points are the light curve in arbitrary units. So basically, this is the this is higher state, and the flux drops a little bit here. And this is the optical depth of the edge. So basically, we don't have a very strong absorption here in this part of the light curve. And albeit with very large errors, we see some rise of these features here. So we hope to be able to track it with much more precision once we add basically, we are missing 3 years of data here, so we hope to track this optical depth with more precision, and this will refine the location of this wind. So I think I will leave the summary and future for Marker 935 here, but thank you for your attention, and I'll take questions.
Any question or comment?
You can ask me a question informally as well.
Ensenada, do you have any question or comment?
No, everything was clear. Thanks. Thanks, Analia.
Thanks, Hector.
Okay, we thank Ana Lilia for the presentation.